Welcome to day 8 of our Principles of Programming Languages course. Today we will be exploring the concept of type safety and type checking. In this session, I will guide you through these important topics that ensure our programs run reliably and safely. Let's begin by defining what we mean by type safety. Type safety refers to ensuring that operations in a program are performed on compatible data types. In simpler terms, it prevents errors caused by mismatched data types, enhancing the robustness and reliability of the code. This is a crucial feature in many programming languages as it helps reduce runtime errors and maintain program correctness. Type safety is not just a theoretical concept, it's a practical necessity in modern programming. Some languages like Java and Python ensure a degree of type safety by enforcing rules about how types interact. Other languages like Haskell are known for their strong type systems which help prevent a wide range of bugs. Next, let's explore the difference between compile time and runtime type checking. In compile time checking, the compiler verifies that types are correct before the program runs. This helps check errors early in the development process. On the other hand, runtime type checking happens when the program is running. Errors are caught only when an operation is attempted on incompatible types. This type of checking allows for more flexibility as seen in dynamically typed languages like Python and JavaScript. However, it can lead to errors that are only detected when the code is executed, making debugging more challenging. Let's look at an example of type errors. In C++, if you try to assign a string value to an integer variable, the compiler will flag it as an error during the compilation process. For instance, declaring an integer and assigning it a string will result in a compilation error because the types are incompatible. In Python, this kind of error can occur at runtime. If you try to add a string to an integer, Python will throw a runtime error saying the operands are of incompatible types. These kinds of errors are harder to catch compared to compile time errors because they only show up during execution. Now let's talk about static versus dynamic type checking. Static type checking occurs at compile time, ensuring that type-related errors are caught before the program runs. In statically typed languages like C++ or Java, the compiler checks for type correctness during compilation, helping to prevent type mismatches. Dynamic type checking, however, happens during the program's execution. In dynamically typed languages such as Python or Java, you can change the type of a variable during runtime and the language will not enforce type checking until the operation is performed. This provides more flexibility but can result in runtime errors if types are mismatched. Type inference is another interesting feature that helps ensure type safety. It's the ability of a programming language to automatically deduce the type of a variable without needing explicit type annotations. For example, in C++, you can use the auto keyword and the compiler will infer the type of the variable based on its assigned values. In Python, the type is inferred at runtime. If you assign an integer to a variable, Python infers it as an integer. Later, if you assign a string to the same variable, it infers the type as a string. While this makes the code more flexible, it also requires careful attention to avoid type-related issues. There are several mechanisms to maintain type safety in programming languages. One of the most common is type annotations. Type annotations allow you to explicitly define the data types of variables or functions or function parameters. In Python, for example, you can annotate the types of function arguments to make the code easier to understand and debug. Another mechanism is strict type mode, which enforces the use of specific types. TypeScript is an example of a language that enforces strict typing, helping prevent issues that arise from dynamically typed languages. Additionally, some languages use runtime validators, which are libraries that check types during execution to ensure that type safety is maintained. Let's touch on some advanced topics in type safety. Subtyping is an important concept. It allows you to use a subtype where a subtype is expected, enabling more flexibility while still maintaining type safety. For example, a method that accepts an object of type shape can also accept objects of type circle or rectangle if they intend from the if they inherit from the shape class. Polymorphism is another key concept that can affect type safety. It ensures that different types can be handled in a uniform way without breaking the type rules. Lastly, generics and type constraints in languages like Java and C# allow you to create flexible yet type-safe code by restricting the types that can be used with generics. To summarize, type safety is a crucial concept that ensures operations are performed on the compatible data types, preventing errors in your program. Compile time and runtime type checking each have their benefits, and type inference, annotations, and strict typing help ensure that type safety is maintained. By understanding and applying these principles, you can write more reliable and bug-free code.